A point of infinite density hides within every black hole. We are about to cross the ultimate boundary to discover what lies inside these cosmic monsters. By the end of our journey, you will understand how new telescopes and quantum theories are finally revealing the black hole's deepest secrets. We will venture past the point of no return and confront a place where time shatters and space folds. Is the heart of a black hole a gateway to another universe, or the end of everything? What does it feel like to question the very fabric of reality? This invisible boundary is the event horizon, the gateway to the unknown. It is not a solid wall you could touch, but a point of no return in the fabric of space itself. Think of it as a one-way membrane. Once anything, even light, crosses this line, it can never come back out. This is the ultimate cosmic cliff edge. The event horizon marks the limit of everything we can possibly see from the outside. It is where our telescopes go blind, and our understanding of spacetime is pushed to its breaking point. For a simple, non-spinning black hole, this boundary is defined by its Schwarzschild radius. This was a pivotal discovery stemming from Einstein's theory of general relativity. A mathematical prediction that revealed these points of no return were real consequences of his equations. Once you cross this threshold, the very nature of reality changes. All possible paths, every direction you could possibly travel, now lead inexorably inward, toward the black hole's mysterious heart. It is like being in a raft that has drifted over the edge of a colossal waterfall. For a moment, you might be right at the precipice, but the current is already pulling you. You have passed the point where you could ever paddle back upstream. The pull of gravity becomes your entire universe. Prominent physicists like Kip Thorne have described the event horizon as exactly that, a one-way street into the black hole's interior. This forces a profound question upon us. What truly happens to a star, a planet, or a particle of light once it passes this point? Does it simply vanish from our universe, or is its story just beginning? To find that answer, we must look beyond this gateway, into the even more mysterious regions that lie within. This one-way street leads to a force of unimaginable violence. As you cross the event horizon, you might not immediately notice anything strange, but the true power of the black hole is about to reveal itself in a process scientists call spaghettification. This is the work of tidal forces, the same kind of gravitational tug that our moon exerts on Earth's oceans to create the tides. But near a black hole, these forces are magnified to an extreme degree by the incredible curvature of spacetime. The difference in gravity's pull over a short distance becomes catastrophic. Think of it like pulling on a piece of taffy. If you grip both ends and stretch, the middle becomes thin and long. That is exactly what happens to anything venturing too close to a black hole's heart. The force on your feet, if you were falling in feet first, would be immensely stronger than the force on your head, just a couple of meters away. Your entire body would be stretched lengthwise into a long, thin stream of atoms. Stephen Hawking brilliantly brought this terrifying idea into popular science, giving a vivid name to a profound physical truth. For an astronaut, the experience would be both swift and gruesome. In a matter of seconds, a human form would be transformed into a strand of spaghetti, a single line of particles all falling toward the same destination. This violent stretching is a direct consequence of the black hole's mass warping the space around it so severely. It is a fundamental demonstration that you are not just falling through empty space. You are falling through space that is itself being twisted and torn. This dramatic transformation underscores the raw, destructive power that defines the journey inward, a journey that is only just beginning. Beyond the violent stretching of tidal forces lies another, even stranger region, one that defies our everyday intuition. Rotating black holes, described by the mathematics of Roy Kerr, possess a remarkable feature just outside their event horizon called the Ergosphere. This is not a place of calm. but a cosmic whirlpool where spacetime itself is dragged into a furious spin. The black hole's immense rotation pulls the fabric of the universe around it, forcing everything within this oval-shaped region to move. This phenomenon, known as frame dragging, was a key prediction of Einstein's theory. It means that within the ergosphere, it is impossible to stand still. No matter how powerful your rockets, you would be swept along in the current of rotating spacetime, like a leaf caught in a tornado. This relentless motion holds a secret, a theoretical possibility for an almost unimaginable power source. Physicist Roger Penrose envisioned a clever way to tap this energy, a method now called the Penrose process. Imagine a spacecraft enters the ergosphere and releases a payload. One piece is deliberately sent crashing into the black hole, following the inward flow of spacetime, while the other piece uses the rotational energy to catapult itself back out. The piece that escapes would actually carry away more energy than the original spacecraft had when it entered. It is a cosmic trick, a way to steal energy from the black hole's own spin. This is not magic, it is pure physics, a consequence of the bizarre way rotation warps reality. The ergosphere becomes a swirling vortex of potential, a testament to the fact that black holes are not just simple destroyers. They are dynamic engines, and understanding their mechanics could one day point us toward advanced technologies, turning the most extreme objects in the cosmos into beacons of possibility. Past the spinning chaos of the ergosphere, the true journey begins. You have crossed the event horizon, the gateway of no return, and now you are inside the black hole. Here, the universe as you know it ceases to exist. The rules of space and time are not just bent, they are fundamentally broken. Inside this mysterious realm, the very roles of space and time are inverted. The direction toward the center is no longer a choice you can make. It is your future. Just as you are pulled inexorably from one second to the next in the outside world, inside the black hole you are pulled from one point to the next, inevitably downward. The radial distance to the center becomes time-like. You cannot stop your motion toward the heart of the black hole any more than you can stop your own aging. It is a one-way street through the fabric of reality itself. For theoretical black holes with charge or spin, the interior may hold another strange boundary, an inner horizon. This is a hypothetical surface where all the radiation and matter that has ever fallen into the black hole could theoretically pile up. It might appear as a wall of blinding, accumulated energy from the entire history of the cosmos. Yet most physicists believe this inner horizon is unstable, a mathematical artifact that would not survive in a real universe, collapsing instantly into the true core of the object. According to the classical rules of Einstein's general relativity, your journey has only one possible ending. You are being funneled, squeezed, and directed toward a single point, the final destination for everything that enters. It is like being in a room where the walls, the floor, and the ceiling are all rushing inward, and the only place to go is the exact center of the collapse. There is no exit, no alternate path. Every possible direction you could turn leads you closer to that ultimate point. This is where our greatest theories of the cosmos collide and shatter. General relativity, which so perfectly describes the gravity warping space, predicts this inevitable collapse into an infinitely dense point. But quantum mechanics, the rules of the very small, suggests that such a point of infinite density is impossible. The two pillars of modern physics give us two completely different and conflicting answers for what happens at the very end. This unresolved conflict is the greatest problem in theoretical physics, and it means that to understand the final fate of anything falling into a black hole, we must confront the ultimate mystery that lies at its very center. At the end of this inevitable collapse lies the singularity. This is the true heart of the black hole, a point where all the mass is crushed into an infinitely small, infinitely dense speck. Our most trusted map of the cosmos, Einstein's general relativity, leads us directly to this conclusion. The mathematics tells us that the curvature of spacetime here becomes infinite. The very fabric of reality, the stage upon which the universe plays out, develops a tier. It is the ultimate breakdown of physics, the equivalent of a calculator trying to divide by zero. The machine simply spits out an error because the operation has no meaning in our logical framework. At the singularity, the concepts of here and there, of before and after, cease to have any definition. This presents a terrifying prospect, a point of infinite power where the laws of cause and effect could simply unravel. What would happen if such a naked singularity, one not hidden from view, existed in our universe? The unpredictable physics at its core could ripple outward, making the future fundamentally random and uncalculable. To prevent this cosmic chaos, physicist Roger Penrose proposed the cosmic censorship hypothesis. This is the idea that nature abhors a naked singularity and always wraps them in the protective cloak of an event horizon. The horizon acts as a firewall, not for heat, but for unpredictability, shielding the orderly universe outside from the lawless infinity within. But this hypothesis forces us to ask a deeper question. Does this mathematical infinity represent a real physical object, or does it simply reveal the limits of our own theories? Can we truly conceive of infinite density, a place where a star's entire mass is compressed into a volume of zero? The very fact that our best model of gravity ends in such an absurdity is a powerful clue. It is a sign that we are missing a crucial piece of the puzzle, a new set of rules that must take over when gravity becomes this extreme. To find those rules, we must look beyond Einstein's masterpiece, into the strange and probabilistic world of the quantum. This mathematical breakdown at the singularity is a powerful signal. It tells us that our understanding of gravity, while brilliant, is incomplete. To solve this ultimate cosmic puzzle, we must venture into the realm of the incredibly small, where the rules are governed by quantum mechanics. The quest to understand what truly lies inside a black hole is the very same quest to find a theory of quantum gravity, a single framework that unites the vast world of planets and stars with the fuzzy, probabilistic world of atoms and particles. General relativity gives us the infinitely dense point, but quantum mechanics abhors such infinities. In the quantum world, everything is granular, everything has a limit. You cannot have infinite density for the same reason you cannot have a digital photograph with infinite resolution. Zoom in far enough on any picture, and you will eventually see the individual pixels. The quantum universe suggests that spacetime itself might be pixelated at the tiniest of scales, preventing the infinite curvature of a singularity from ever forming. This idea has led physicists to propose spectacular alternatives for the black hole's core. One compelling idea comes from string theory, where the fundamental building blocks of reality are not points, but tiny, vibrating strings. Theorists like Leonard Susskind have proposed that a black hole might not contain a singularity at all. Instead, its interior could be a gigantic, tangled ball of strings, a structure they call a fuzzball. This fuzzball would have a definite, though immense, density and a complex structure, effectively smearing out the sharp, mathematical point into a fuzzy quantum object. There would be no point of infinite density, only a dense, exotic star made of the very fabric of spacetime. Another path is explored in loop quantum gravity, championed by scientists like Carlo Rovelli. This theory suggests that the crushing collapse of matter does not end in a singularity, but instead triggers a quantum bounce. Imagine the core of the black hole reaching a point of such extreme density that quantum pressures become unimaginably strong, acting like a cosmic cushion. Instead of collapsing to nothing, the matter rebounds, spewing its contents back out. But where could it go? One extraordinary possibility is that this bounce creates a white hole, the theoretical opposite of a black hole, violently expelling matter and light. This white hole could even be the birth of an entirely new universe, a baby cosmos connected to our own through the quantum tunnel of a black hole's heart. These are not just wild speculations. They are serious attempts to resolve the greatest conflict in physics. Black holes are the ultimate testing grounds, the cosmic laboratories where our most fundamental ideas about reality are pushed to their absolute limits. They force us to ask whether the heart of darkness is truly an end, or if it is a transformation so profound that it rewrites the story of the cosmos itself. This paradox strikes at the very foundation of physics. At its core is a simple but unbreakable quantum rule. Information can never be truly destroyed. You could burn a priceless book, turning its pages to smoke and ash. The book is gone, but in principle, if you could collect every single atom of smoke and ash and track their movements with perfect precision, you could reconstruct every word. The information has merely been scrambled, not erased. Now, place that book into a black hole. According to Stephen Hawking's groundbreaking work in the 1970s, the black hole will slowly evaporate, fading away over eons by emitting a faint glow we now call Hawking radiation. Hawking calculated that this radiation is entirely random, carrying no information about what fell in. When the black hole finally vanishes, the information about that book, and everything else it ever consumed, would vanish with it. Gone forever. This was Hawking's shocking claim that black holes are the ultimate shredders, violating a sacred principle of quantum mechanics. The physics community was thrown into chaos. If Hawking was right, our entire understanding of the quantum universe was fundamentally flawed. This was the birth of the black hole information paradox, a battle between the two greatest theories of physics played out on the edge of a gravitational abyss. The debate raged for decades, forcing physicists to question their deepest assumptions. Where does the information go? The resolution may be even stranger than the paradox itself. Perhaps the information is not lost at all. Physicists like Gerard T. Hooft and Leonard Susskind proposed a revolutionary idea. What if the information from the book is not destroyed inside the black hole, but is instead perfectly encoded or painted onto the two-dimensional surface of the event horizon? Then, as Hawking radiation escapes, it reads this information from the surface, carrying it back out into the universe in a vastly complex code. It would be as if the smoke from our burning book reassembled itself, particle by particle, into a perfect copy of the original. This line of thinking leads to one of the most profound concepts in modern physics, the holographic principle. It suggests that our perception of a three-dimensional reality of depth and volume inside the black hole might be an illusion. All the information needed to describe everything within that vast interior could be stored on the two-dimensional boundary that surrounds it. Much like a hologram on your credit card encodes a three-dimensional image on a flat, plastic surface. The black hole is not a cosmic trash can. It is potentially the most efficient information storage device in the universe, and its event horizon is the hard drive. This paradox forces us to accept that our classical ideas of space and location are incomplete. The information was never inside the black hole in the way we thought. It was always on the surface, waiting for a quantum mechanism to reveal its secrets, challenging everything we assume about where things are and what reality truly is. The holographic principle takes this idea of information on the surface to its ultimate, breathtaking conclusion. It proposes that our entire three-dimensional universe, with all its depth and volume, might be a projection from a two-dimensional surface at its boundary. Think of a security hologram on your credit card. The image has stunning depth, you can look around it, but all the information to create that illusion is encoded on the flat, two-dimensional sticker. The holographic principle suggests our reality works in a similar way. For a black hole, this means the entire vast interior, the crushing depths and the mysterious core, might not be the fundamental reality. Instead, it is an emergent illusion, a three-dimensional movie projected from the quantum data, painted on the two-dimensional screen of the event horizon. This radical idea found its roots in the work of physicists like Jacob Bekenstein and Stephen Hawking. They discovered that a black hole's entropy, which is a measure of its hidden information content, is not proportional to its volume as you might expect. It is proportional to the area of its event horizon. This was a profound clue. It hinted that the true degrees of freedom, the basic bits of information that describe everything inside, were all living on the surface. Gerard T. Hooft and Leonard Susskind took this clue and ran with it, formally proposing that the universe might be fundamentally two-dimensional, a concept that feels almost impossible to grasp. This is not just a philosophical curiosity. In string theory, we find a concrete mathematical realization called the AD-SCFT correspondence. It provides a perfect dictionary. It tells us that a gravitational theory describing a volume of space, like the interior of a black hole, is completely equivalent to a quantum field theory living on its lower dimensional boundary. We can use this powerful tool to translate impossibly difficult questions about gravity inside the black hole into more manageable questions about quantum particles on its surface. The crushing singularity, the folded spacetime, the very experience of falling in, all of it could be a direct consequence of complex quantum interactions happening on a distant, flat screen. This reshapes our view of reality itself. The interior of a black hole may not be a place you can travel to in the traditional sense. It is an emergent structure, a story written in quantum code on the event horizon's surface, a story so rich and complex that it generates the illusion of a vast, three-dimensional world within. If this is true for a black hole, could it also be true for our entire cosmos? Are we, and everything we see, just a holographic projection from the edge of the universe? The silent cosmos has begun to speak. For decades, black holes were the ghosts of the universe, detected only by their shadowy influence on nearby stars and gas. But everything changed in September 2015, when humanity heard its first cosmic symphony. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected a faint chirp, a ripple in the very fabric of spacetime that had traveled for 1.3 billion years to reach us. It was the sound of two black holes, each about 30 times the mass of our Sun, performing their final deadly dance. They spiraled inward at nearly the speed of light and collided, merging into a single, more massive object. In that cataclysm, an amount of energy equivalent to 3 times the mass of our Sun was converted into pure gravitational waves in a fraction of a second. Kip Thorne, a key architect of LIGO, described it as a violent storm in the fabric of space and time, a storm that was fleeting, lasting only a few tenths of a second. We are no longer just astronomers, we have become listeners. Think of throwing a pebble into a still pond. The ripples that spread out carry information about the pebble, its size, and the force of its impact. Gravitational waves are the ripples from the most violent events in the universe, and by studying their shape and frequency, we can understand the nature of the objects that created them. The detailed analysis of these signals tells us the masses of the colliding black holes, how fast they were spinning, and even provides clues about the stability of their event horizons during the immense collision. This new window has revealed a universe teeming with black holes of sizes we never expected, building a census of dark objects we could never see with light. Every merger we listen to is a direct test of Einstein's general relativity in the most extreme gravitational fields imaginable, but the potential goes even deeper. Some physicists speculate that the ringing of the new, merged black hole might not be perfectly clean. If the event horizon has a quantum structure, like a fuzzy or tangled surface, it could produce faint echoes in the gravitational wave signal, subtle whispers following the main crash. We are now collecting these cosmic sounds, building a library of collisions that may one day contain the first direct evidence of what truly happens at the edge, and perhaps even the interior of a black hole. These faint whispers following a gravitational wave crash could be the most important sound in the universe. They are called black hole echoes, and they are the target of a daring scientific hunt. When LIGO hears the main ringdown of a newly formed black hole, the signal we get is almost perfectly described by Einstein's theory. It is the sound of a smooth, featureless event horizon settling into its final form. But what if that horizon is not smooth? What if, on the tiniest possible scale, it has a structure? In several quantum gravity models, the classical event horizon is replaced by something else entirely. It might be a quantum horizon, a region of intense energy acting like a firewall, or a tangled fuzzball surface. These theoretical structures would not be perfectly black. They could reflect a tiny portion of the gravitational energy sloshing around inside the newborn black hole. Imagine sending a sonar ping into the deep ocean. The main ping reflects off the seafloor, but if there is a hidden submarine or a sunken city in its path, you will hear a fainter, delayed echo. The quantum structure of a black hole could act in the same way. The main gravitational wave signal is the direct ping from the merger, but a fraction of the energy might bounce off this exotic inner structure, travel back out, and be reflected again, finally escaping a moment later. This creates a faint, repeating echo in the data, a ghostly signature hidden in the noise. Theorists like Nyashev Shorty have pioneered the search for these signals, developing sophisticated algorithms to comb through the public data from LIGO and its European counterpart, Virgo. They are looking for a specific pattern of repeating whispers that would betray the presence of a physical surface, just inside where the event horizon should be. Finding even a single, confirmed echo would be a monumental discovery. It would be our first direct observational evidence that Einstein's picture is incomplete at this boundary. We would have proven that something new and quantum mechanical exists at the edge of a black hole, giving us an experimental handle on quantum gravity itself. This is no longer pure philosophy or abstract math. It is data-driven science, a direct test of whether the universe operates with smooth horizons or a pixelated quantum reality. The echoes we seek are the vibrations of spacetime itself, ringing against the fundamental grain of the cosmos. These faint echoes are the target of a global hunt, but we are not waiting passively for nature to provide the answers. Scientists are now building their own black holes inside the world's most powerful supercomputers. These are not physical objects, of course, but incredibly complex digital simulations that solve Einstein's fiendishly difficult equations for scenarios we can never hope to witness firsthand. Think of it as a flight simulator for the cosmos. Before test, pilots risk their lives in a new aircraft. They spend countless hours in a virtual cockpit, pushing the plane to its limits in conditions that would be far too dangerous in reality. Numerical relativity, the field dedicated to this work, does the same for spacetime itself. It allows researchers to crash black holes together, spin them at near light speed, and send virtual probes across event horizons, all from the safety of a computer lab. These simulations are not simple animations. They are massive mathematical experiments that divide the fabric of spacetime into billions of points, calculating how each point curves and evolves over trillionths of a second, according to the rules of general relativity. The calculations are so immense that they can tie up a supercomputer for months, churning through numbers to produce a few seconds of cosmic drama. Landmark projects like the Simulating Extreme Spacetimes Collaboration, or SXS, have produced breathtakingly accurate visualizations of black hole mergers. Their work gives us the iconic imagery of two dark shadows spiraling in a storm of warped starlight, visuals that were crucial for interpreting the gravitational wave signals detected by LIGO. Computational relativists like Franz Pretorius were pioneers, achieving the first full simulation of a black hole merger in 2005. His work cracked a problem that had stumped physicists for decades, showing how the violent collision of two event horizons settles into the single, quivering bell of a new black hole. These virtual experiments are essential guides. When LIGO hears a chirp from a billion light-years away, it is the supercomputer simulations that tell us what kind of collision must have caused it. They are now pushing into the final frontier, modeling the chaotic interior of a black hole itself. By simulating the journey of hypothetical particles and fields past the point of no return, these digital laboratories offer a glimpse into how spacetime might churn and fold within. They test whether quantum pressures could halt a collapse or if the journey truly does lead to a singularity. Every simulation is a question posed to the universe, a digital thought experiment that brings us one step closer to understanding the absolute limits of reality. Deep within the mathematics of general relativity, another ghostly structure appears, a tunnel through the cosmos. These are wormholes or Einstein-Rosen bridges, hypothetical shortcuts connecting two distant points in spacetime. Imagine our universe is the surface of a vast apple. An ant walking along the curved surface has a long journey from one side to the other, but a worm, tunneling directly through the apple's core, takes a much shorter path. A wormhole is that tunnel, a bridge through the higher dimensions of spacetime that could, in theory, make a journey of a billion light-years almost instantaneous. The equations of Einstein and his colleague Nathan Rosen revealed that the same warping of space that creates a black hole could also, under very specific conditions, form a tunnel to another location, or perhaps even to another universe entirely. Unlike a black hole, which is a one-way street ending in a potential singularity, a wormhole would have no central point of infinite density. It would be a throat, a passageway connecting two mouths. You could, in theory, travel through it in both directions, emerging light years from your starting point. Think of it as the difference between driving off a cliff and driving through a mountain tunnel. One is a fatal drop, the other is a convenient shortcut. The great physicist John Wheeler, who first coined the charming name wormhole, helped bring these ideas into the scientific mainstream. Yet for all their theoretical elegance, there is a monumental catch. These spacetime tunnels are catastrophically unstable. According to the classical equations, the moment even a single photon of light tries to pass through the throat, the wormhole would pinch off like a bursting soap bubble, collapsing faster than the speed of light. The tunnel would snap shut, leaving the traveler stranded or worse. To prop this tunnel open, to create a stable gateway for travel, would require something truly bizarre, exotic matter. This is not just unusual stuff like dark matter. Exotic matter would need to possess negative energy density, effectively generating a form of antigravity that pushes the walls of the wormhole apart, preventing its collapse. While tiny amounts of negative energy might be possible through quantum effects like the Casimir effect, the quantities needed to stabilize a human traversable wormhole are astronomical and may be completely impossible. This has not stopped brilliant minds from exploring the implications. Kip Thorne and his students famously investigated whether such a stable wormhole could be used as a time machine, a concept that rigorously followed the laws of physics as we understand them, even if it required fantastical materials. This is where black hole physics truly expands our imagination, pushing into realms that feel like science fiction. The very fact that our best theory of gravity allows for such structures, even if they are unrealizable, forces us to confront the deepest nature of reality. Are these cosmic shortcuts merely mathematical curiosities, or do they hint at a far more connected, and far stranger, cosmos than we have ever dared to dream? If you could run the cosmic film of a black hole in reverse, you would witness a white hole. This theoretical object is the exact opposite of its dark twin. Where a black hole's event horizon acts as a one-way street inward, a white hole's boundary is an absolute exit door. Nothing from the outside can ever get in, while everything from within is violently expelled in a torrent of matter and radiation. General relativity's equations are time-symmetric, meaning they work just as well whether time flows forward or backward. And white holes are the mathematical result of playing a black hole's life in rewind. They are perfectly valid solutions, yet most physicists doubt they exist in our universe. The problem is one of creation. We know how black holes form from the collapse of massive stars or the merger of dense objects. But what natural process could possibly birth a white hole? A cosmic fountain that has been spewing since the beginning of time without ever being fed. There is no known mechanism, which relegates them to the realm of beautiful, speculative thought experiments. However, the story does not end there. When we introduce the rules of the quantum world, white holes transform from a mathematical curiosity into a potential cosmic reality. In loop quantum gravity, a theory championed by Carlo Rovelli, the terrifying singularity at a black hole's heart is not the end. Instead, the immense quantum pressure at the core acts like an impenetrable cosmic cushion. The collapse does not continue to an infinitely dense point, but reaches a maximum density and then rebounds. This quantum bounce would transform the black hole into a white hole. The matter that fell in over billions of years would not be lost forever. After a tremendously long time, the black hole would effectively turn inside out, erupting and releasing all that stored material back into the cosmos. This is not a fast process. For a black hole with the mass of our Sun, the transition would take much longer than the current age of the universe. For a larger black hole, the wait would be exponentially greater. You could never see it happen, but as a theoretical endpoint, it offers a profound resolution. It suggests that black holes are not eternal prisons, but are instead temporary, if incredibly long-lived, waystations in the life cycle of matter. The existence of white holes would force us to completely rewrite our understanding of causality. If a black hole can become a white hole, then what goes in must eventually come out. The one-way street becomes a cosmic roundabout, with matter entering through one door and leaving through another, perhaps into a different region of space-time altogether. This idea challenges the very arrow of time within these extreme objects, pushing us to ask the final question about the ultimate destiny of every black hole in the sky. The profound link between information and a black hole's surface hints at an even deeper truth, one that connects these dark objects to the most familiar of forces, heat. A black hole, it turns out, obeys the laws of thermodynamics. It has entropy, and most shockingly, it has a temperature. This realization began when a young physicist named Jacob Bekenstein made a daring proposal. He argued that a black hole's entropy, which is a measure of its hidden information or disorder, is proportional to the area of its event horizon. The larger the black hole, the more surface area it has, and the greater its entropy. This was a radical idea because in every other system we know, entropy is related to volume. But for a black hole, all the information that falls in seems to be painted on its two-dimensional boundary, and the size of that canvas determines how much it can hold. Stephen Hawking initially disliked this idea. If a black hole has entropy, then by the fundamental rules of thermodynamics, it must also have a temperature. And any object with a temperature must emit radiation. But how could anything escape a black hole's grip? Hawking set out to prove Bekenstein wrong, but in doing so, he made one of the most celebrated discoveries in modern physics. He found that Bekenstein was right. By applying quantum theory to the empty space just outside the event horizon, Hawking discovered that black holes do indeed glow. Empty space is not truly empty. It is a seething quantum foam where pairs of virtual particles, one with positive energy and one with negative energy, constantly flicker in and out of existence. Usually, they annihilate each other almost instantly. But right at the edge of a black hole, a strange theft can occur. If one of these virtual particles falls across the event horizon, its partner is left stranded outside. Robbed of its chance to annihilate, the orphaned particle becomes real, escaping into the universe as a tiny bit of radiation. This is Hawking radiation. To an outside observer, it looks as if the black hole itself is glowing, like a hot coal in the cosmic night. This glow is incredibly faint for a large black hole, far colder than the background temperature of the universe. But it carries energy away, and that energy has to come from somewhere. It comes from the black hole's own mass. Over astronomical timescales, a solitary black hole slowly loses weight, shining its substance away particle by particle. Hawking himself was stunned by this result, calling it the most surprising discovery of his career. He had reconciled gravity with thermodynamics, but at a great cost. This evaporation process leads to a profound dilemma. If the black hole eventually vanishes in a final puff of Hawking radiation, what happens to all the information about the stars, planets, and atoms it consumed over its lifetime? According to Hawking's original calculation, the radiation is purely thermal, random, and featureless. It carries no information. The black hole would be the ultimate furnace, incinerating the cosmic library into meaningless heat. This was the birth of the information paradox, a puzzle that would haunt physics for decades. The Bekenstein-Hawking formula, which gives the precise entropy of a black hole, sits at the heart of this mystery. It tells us that entropy, and therefore information, is tied directly to the area of the event horizon in units of the Planck scale. This is not just a number. It is a fundamental statement about the quantum structure of spacetime. It suggests that the universe keeps its accounts in bits of information painted on surfaces, and that gravity is the emergent consequence of this quantum data. This thermodynamic perspective transforms the black hole from a simple hole in space into a dynamic quantum object with a life cycle, one that is slowly burning away into the void, forcing us to confront the ultimate question of what remains when the fire finally goes out. While everything we have explored so far comes from the collapse of massive stars, there is another, even more ancient kind of black hole that might be hiding in the cosmic shadows. These are primordial black holes, and they are not born from dying suns, but are instead relics of the universe's violent infancy. In the first fleeting moments after the Big Bang, the entire cosmos was a seething, dense, and turbulent soup of energy. Within this chaos, some regions could have been squeezed to an incredible density by random fluctuations. Think of a pot of water just beginning to boil. Bubbles form spontaneously as regions of lower density vapor appear within the hotter liquid. In the early universe, pockets of space could have become so densely packed with energy that their own gravity caused them to directly collapse, bypassing the need for a star entirely. This elegant hypothesis was championed by visionaries like Stephen Hawking and Bernard Carr, who realized these objects could be almost anything in size. A primordial black hole could be as small as an asteroid, with the mass of a mountain compressed into a space smaller than an atom. Or it could be as colossal as the supermassive giants we find at the centers of galaxies today. Their potential existence forces us to rethink the very composition of the cosmos. What if the mysterious dark matter that holds galaxies together is not made of exotic, unknown particles, but is instead the collective gravity of countless trillions of these ancient, invisible black holes drifting between the stars? This is a compelling idea, as they would interact only through gravity, just as dark matter is observed to do. To hunt for these phantoms, astronomers use clever tricks. One method is called microlensing. If a small, dense primordial black hole were to pass directly between Earth and a distant star, its gravity would act as a lens, bending the starlight and causing the star to temporarily brighten. Vast surveys of the sky constantly monitor millions of stars, watching for these characteristic flashes. Other searches look for the subtle imprint these black holes would have left on the cosmic microwave background, the ancient light from the dawn of time. Their formation would have created ripples in this primordial radiation, a faint signature we might still be able to detect. The most startling possibility is that these objects could be much closer than we imagine. A small, asteroid-mass primordial black hole could, in theory, be orbiting silently in the outer reaches of our own solar system. Its presence betrayed only by the unexplained gravitational tug on distant comets or probes. Finding one would be like discovering a fossil from the very first second of creation, a direct messenger from the birth of the universe, offering clues about the conditions that forged reality itself. Our own cosmic backyard holds a sleeping giant. 26,000 light-years away, at the very heart of the Milky Way, lies a supermassive black hole named Sagittarius A star. This colossal object contains the mass of 4 million suns compressed into a region smaller than our solar system. For decades, its presence was a compelling theory, but the proof came from watching the frantic dance of stars around an invisible point. Astronomers like Andrea Ghez and Reinhard Genzel dedicated their careers to this celestial choreography. For over 20 years, their teams trained the world's most powerful telescopes on the galactic center, meticulously tracking the orbits of individual stars. They saw these stars whip around an empty spot at breathtaking speeds, some completing their oval-shaped orbits in just a few Earth years. One star, known as S2, reached a velocity of over 15 million miles per hour at its closest approach. This was like watching a swarm of fireflies circling an invisible, massive pivot in the dark. The precision of these orbits, much like planets around a sun but on a far more violent scale, provided irrefutable evidence of a supermassive black hole's gravity, a discovery that earned Ghez and Genzel the Nobel Prize in Physics. This gravitational grip is our greatest laboratory. By studying how Sagittarius A star pulls on its stellar neighbors, we can test Einstein's theory of relativity under extreme conditions and understand how such a behemoth influences the evolution of an entire galaxy. Then, in 2022, we saw it. The Event Horizon Telescope collaboration, a global network of radio observatories working as one Earth-sized dish, released the first-ever image of Sagittarius A star. It was not a picture of the black hole itself, for that is impossible, but of its shadow. The image shows a brilliant, fiery ring of light surrounding a dark central region. This ring is the photon sphere, a region where gravity is so strong that light itself is forced to orbit the black hole. The central darkness is the shadow cast by the event horizon, a void created by the black hole's immense gravitational lensing, which bends all light paths inward, and the point of no return at its edge. This glowing donut of light is the signature of hot, swirling gas just moments before it is lost forever. Sagittarius A star is relatively quiet compared to other supermassive black holes, but it still offers occasional flares and flickers, clues to the chaotic processes of accretion and the mysterious origins of the powerful jets that other black holes fire into space. By observing our local giant, we have a front-row seat to the physics that governs the most powerful engines in the universe. This superheated whirlpool of matter is the black hole's final farewell to the universe it consumes. As gas, dust, and even entire stars are pulled toward the event horizon, they rarely fall straight in. Instead, they possess too much sideways motion, a property called angular momentum, forcing them to spiral inward at fantastic speeds, like water circling a cosmic drain. This swirling river of doomed material forms a vast, flat structure known as an accretion disk. The friction within this disk is unimaginable. Particles grinding against each other generate temperatures that soar into the millions of degrees, causing the entire disk to glow with a ferocious intensity, blazing across the electromagnetic spectrum from radio waves to powerful X-rays. This is the light that our telescopes, like the Chandra X-ray Observatory, actually see, the brilliant, energetic signature of matter in its death throes. But the story does not end with this slow, spiraling descent. Some of this superheated material does not make it into the abyss. The black hole's immense rotation and its powerful, tangled magnetic fields can act like a colossal particle accelerator. They funnel a fraction of the infalling matter into two narrow, opposing beams that blast outward from the black hole's poles, perpendicular to the disk. These are relativistic jets, firing matter at velocities so close to the speed of light that the laws of relativity warp their very appearance from our distant vantage point. Picture that water swirling down a drain, but with a powerful pump attached that forces some of that water to shoot straight back out through a narrow hose, reaching incredible heights. These jets can extend for thousands of light years, punching through entire galaxies and injecting vast amounts of energy into intergalactic space. The Hubble Space Telescope has captured stunning images of these cosmic blowtorches, glowing pillars of energy that can outshine the galaxies that host them. While these spectacular fireworks happen far outside the event horizon, they are a direct window into the black hole's hidden engine. The power and structure of these jets tell us about the black hole's spin and the strength of its magnetic fields, properties forged in the mysterious depths we cannot see. By studying the accretion disk's furious light and the jet's incredible reach, we understand how these dark giants are not passive vacuum cleaners. They are active, dynamic forces that can ignite or quench the birth of stars across their home galaxies, shaping the very large-scale structure of the cosmos with the energy generated from their final feast. This elegant simplicity is captured by a profound idea called the No-Hair Theorem. It tells us that an isolated black hole, in the clean world of classical physics, is a fundamentally simple object. It can be completely described by just three numbers: its mass, its electric charge, and its spin, or angular momentum. Every other detail, every shred of information about the stars, planets, and atoms that collapsed to form it or later fell in, is lost to the outside universe. All the complexity, the color of a star, the chemistry of a planet, the words in a book, is seemingly shed beyond the event horizon, leaving behind a bald, featureless gravitational pit. The great physicist John Wheeler, who helped popularize this concept, summarized it beautifully: black holes have no hair. Think of throwing a vast and varied feast into an impossibly powerful blender. You start with unique ingredients: a crisp apple, a spicy pepper, a piece of bread. After the blender roars to life, you are left with a single, uniform smoothie. From the outside, you can only measure the total volume, which is like the black hole's mass. You might detect if the overall mixture is acidic or basic, analogous to a net electric charge. And you could see if the container is spinning, representing angular momentum. But all the intricate details of the original meal are irretrievably scrambled and lost within the mixture. This theorem presents a stark picture, one that sits at the heart of the information paradox. If a black hole is truly this simple, then the information about what fell in is not just hidden, it is permanently erased from our universe, violating a core principle of quantum mechanics. Yet this very conflict points toward a resolution. The No-Hair Theorem is a prediction of classical general relativity, but our universe is quantum. Physicists now strongly suspect that quantum corrections must violate this perfect simplicity. The information is not truly lost. Instead, it might be stored in incredibly subtle ways, perhaps encoded in the quantum fluctuations of the event horizon itself. The surface might appear smooth and featureless from a distance, but on the Planck scale, it could be a seething, complex tapestry, preserving every single bit of information that ever crossed it. The journey from a three-parameter description to an infinitely complex quantum system marks the frontier of our understanding, forcing us to see these dark objects not as simple holes in space, but as the most sophisticated information processors in the cosmos. This seemingly perfect solution, however, ignited a firestorm of its own, giving rise to an idea so radical it threatens to burn down our classical understanding of the event horizon entirely. The Firewall Paradox asks a shocking question. What if the event horizon is not a smooth, empty gateway, but a blazing wall of energy that instantly vaporizes anything attempting to cross? This incendiary proposal was born from a desperate attempt to resolve the information paradox with absolute purity. A team of physicists including Ahmed Almeri and Donald Marolf argued that for information to be perfectly preserved and for quantum unitarity to be upheld, the entanglement between particles must be severed with extreme prejudice at the horizon. The most dramatic way to sever that quantum connection is with an unimaginable release of energy, a literal firewall that burns away the past and resets the cosmic ledger. Imagine stepping through what looks like an ordinary doorway, only to find yourself instantly consumed by a wall of searing flame on the other side. For an astronaut falling toward a black hole, the classical view promises a quiet, uneventful crossing. The equivalence principle of general relativity assures us that a free-falling observer should feel nothing special, noticing no local difference as they pass the point of no return. But the firewall shatters this foundational principle. It suggests the event horizon is not a place of calm, but a region of violent, fundamental disruption. The arguments against firewalls are equally powerful, rooted in the very success of Einstein's theory. Violating the equivalence principle is not a small matter. It would mean that our most trusted description of gravity is profoundly wrong in its prediction of what happens at this critical boundary. Critics argue that such a drastic solution creates a problem far worse than the one it tries to solve, replacing a subtle information paradox with a blatant, energetic contradiction. This ongoing debate is not just academic. It represents a fundamental clash between the smooth, geometric reality of general relativity and the discrete, informational reality of quantum mechanics. The firewall forces us to choose. Do we sacrifice the gentle fall predicted by Einstein to save the quantum rulebook? Or do we seek a more subtle, less violent reconciliation? The event horizon, it seems, is not just a boundary in space, but a frontier in our understanding, where the laws of physics themselves are put to the ultimate test. The same gravity that creates a black hole's shadow might also cast light on the universe's greatest missing piece. For decades, astronomers have known that most of the matter in the cosmos is invisible, a mysterious substance we call dark matter. It does not emit or absorb light, yet its gravitational pull is the only thing holding galaxies together from flying apart. We know it is there, but we have no idea what it is made of. One of the most compelling and surprising candidates comes from the black holes we have been exploring. What if a significant portion of this dark matter is not a sea of exotic particles, but a vast population of ancient, invisible black holes? These would be the primordial black holes, formed in the first chaotic moments of the Big Bang. They could range in size from smaller than an atom to more massive than a star, drifting through the galaxy like a ghostly swarm. The key question is one of numbers. If enough of them exist within a specific mass window, their collective gravity could perfectly account for the dark matter we observe bending light and shaping galaxies. This idea transforms our view of the cosmos, suggesting that the darkness holding galaxies together is not a diffuse cloud, but a constellation of countless tiny, dark pits in spacetime. It is like discovering that the invisible ink on a secret map is not a smooth stain, but is actually composed of trillions of microscopic dots, each one a universe in its own right. How could we possibly test such an extraordinary idea? The answer comes from listening to the collisions of the cosmos. Every time the LIGO and Virgo observatories detect a gravitational wave signal from two black holes merging, They are not just witnessing a cosmic catastrophe. They are taking a census of the dark population. Each event tells us the masses of the colliding black holes. By building up a statistical picture from dozens of these mergers, scientists can begin to rule out certain mass ranges. If dark matter were made entirely of black holes in a specific size category, say between 20 and 100 solar masses, then LIGO should have seen many more mergers in that range than it actually has. The data so far suggests that while primordial black holes could still be a component of dark matter, they cannot be the whole story. They are constrained to certain niches, like only being able to hide in specific corners of the mass spectrum. This is a powerful demonstration of how the new science of gravitational waves is not just about black holes themselves, but is a tool for probing the entire hidden structure of the universe. There is another, more subtle way black holes might reveal dark matter. Imagine a single black hole moving through the galaxy. If dark matter is made of theoretical particles, like WIMP, then these particles would be scattered everywhere, including in the black hole's vicinity. The black hole's immense gravity would act as a trap, pulling in and accumulating a dense, swirling cloud of these dark matter particles around it, much like a massive celestial object gathering a thick atmosphere. This dark matter halo would not be visible, but its presence would have tangible effects. The constant interaction and annihilation of these particles within the cloud could produce a faint but distinctive signal of gamma rays, a high-energy light that our telescopes could potentially detect. Furthermore, as the black hole consumes this dark matter, it could grow in mass at a rate that is subtly different than if it were only eating normal matter, leaving an imprint on the evolution of supermassive black holes over cosmic time. Theorists are actively modeling these scenarios, looking for any anomalous signal from known black holes that could be the fingerprint of their dark matter diet. While the connection remains speculative, it represents a breathtaking synthesis of ideas. The most enigmatic objects in the universe could become our guides to understanding the most elusive substance. By studying the darkness we can see, we may finally learn to see the darkness we cannot. Our cosmic listening posts are about to become vastly more powerful. The next generation of observatories, both on the ground and in space, will transform black holes from distant mysteries into detailed laboratories. Imagine the leap from Galileo's first telescope to the Hubble Space Telescope, a revolution that brought the cosmos into sharp focus. We are on the verge of a similar breakthrough in our study of these dark giants. Leading this charge is the Laser Interferometer Space Antenna, or LISA. This ambitious mission, a trio of spacecraft flying in a perfect triangle millions of kilometers apart, will open a new window on the universe by detecting gravitational waves at frequencies far lower than ground-based detectors can sense. LISA will hear the deep, resonant hum of merging supermassive black holes, events that shook the early cosmos and now govern the growth of galaxies. Project scientists describe LISA as an instrument for listening to the tenor section of the cosmic choir, revealing the slow, grand dances that have been silent until now. On the ground, the extremely large telescope is rising from the Chilean desert. With a primary mirror nearly 40 meters across, it will collect more light than all of today's large optical telescopes combined. The ELT will not just see the stars whipping around Sagittarius A. It will map their orbits with breathtaking precision, testing general relativity in ways previously impossible, and perhaps even spotting subtle distortions in spacetime caused by the black hole's spin. Its powerful spectrographs will analyze the composition and motion of gas in accretion disks, watching the final moments before matter vanishes. In space, the James Webb Space Telescope peers into the infrared, cutting through cosmic dust to study the violent environments around black holes in distant galaxies. It sees the faint glow of ancient accretion disks and the shock waves from relativistic jets, helping us understand how these engines influence star formation across cosmic time. Meanwhile, proposed X-ray missions like Athena and Lynx promise to study the searingly hot plasma just milliseconds from the event horizon, probing magnetic fields and plasma physics in the most extreme gravity imaginable. Together, these technological marvels will do more than just take prettier pictures. They will turn the theoretical into the observable, allowing us to test the wildest ideas about quantum horizons, fuzzballs, and the very nature of spacetime. The silent darkness at the heart of a black hole is about to be illuminated, not by light, but by the brilliant ingenuity of human curiosity. That silent darkness at the heart of a black hole speaks to a fundamental human need, the drive to understand the cosmos and our place within it. This quest is not confined to the halls of academia. It thrives on a partnership between scientists and the public, a shared journey of discovery that inspires the next generation of explorers. Stunning visualizations have become our universal language for these invisible wonders. The first image of a black hole's shadow, a fiery ring against the void, was not just a scientific triumph. It was a cultural moment that ignited global curiosity. These visuals, born from petabytes of data and years of collaboration, translate abstract equations into a shared experience, a testament to what humanity can achieve when we look together. Popular science has built a vital bridge, turning complex theories into compelling narratives. Books by visionaries like Stephen Hawking and documentaries featuring communicators like Neil deGrasse Tyson and Brian Cox have transformed black holes from frightening myths into fascinating puzzles. They use relatable analogies and infectious enthusiasm to demystify the universe, making everyone feel like they have a front-row seat to the greatest show in the cosmos. Perhaps one of the most powerful mergers of science and storytelling was the film Interstellar. With Nobel laureate Kip Thorne as its scientific consultant, the movie presented a black hole, Gargantua, with unprecedented accuracy. The teams of artists and physicists worked for a year to render the light-bending effects of its accretion disk, creating a visualization so precise it led to a published scientific paper. This collaboration brought a scientifically grounded vision of a black hole to millions, proving that realism can be as awe-inspiring as any fiction. Beyond the screen, planetariums and science museums offer immersive portals to the edge of spacetime. Under a domed sky, you can witness the violent dance of binary black holes or take a simulated flight toward the galactic center, experiences that make the scale and power of these objects viscerally real. Online courses from universities and institutions have democratized access, allowing anyone with an internet connection to learn the fundamentals of general relativity from world experts. This outreach is far more than just public relations. It is the lifeblood of fundamental science. Sustained public interest translates into crucial funding for the next great telescope or space-based observatory. More importantly, it plants a seed of wonder in a young mind. The child who sees that first image of a black hole in a planetarium, or the student who joins a citizen science project to classify gravitational wave signals, might be the one who solves the Singularity Paradox tomorrow. Our collective curiosity fuels this entire endeavor, ensuring that the human drive to peer into the ultimate unknown never fades. These cosmic laboratories force us to confront the very limits of knowledge itself. Black holes are not just physical objects. They are philosophical puzzles that challenge our most basic assumptions about reality. What does it mean to understand something that is, by its very nature, hidden behind an impenetrable curtain? We build theories, we run simulations, but the core of a black hole might be fundamentally unobservable, a permanent secret kept by the universe. This pushes science to its boundary, the frontier where empirical data meets profound speculation. It echoes the thoughts of philosophers like Karl Popper, who argued that science advances by confronting the unknown and the potentially unfalsifiable. Our quest to understand black holes is a live experiment in this very process, testing the limits of the scientific method. This journey raises a poignant ethical question. Why should we devote billions of dollars and the finest scientific minds to study objects trillions of miles away, with no obvious practical benefit? The answer lies in the same spirit that drove ancient explorers to set sail into uncharted oceans. They did not know what they would find or if they would return, but they were driven by a fundamental human curiosity, a need to map the unknown. That same drive fuels our cosmic exploration today. The technological spin-offs from this pure research are undeniable. The quest to detect gravitational waves gave us incredibly precise laser measurement tools. The algorithms developed to process LIGO data are now used in medical imaging and financial modeling. Pushing the envelope of quantum gravity might one day unlock understandings of energy and computation we cannot yet conceive. But beyond these tangible benefits, there is a deeper cultural value. By grappling with the infinite and the singular, we are forced to reflect on our own finite place in the cosmos. How does exploring the possibility of other universes or the birth of spacetime change our perspective on human conflicts, on art, on what it means to be alive? These explorations do not provide easy answers, but they enrich our collective imagination, reminding us that we are part of a story far grander than our daily lives. The true value may not be in a final answer, but in the act of asking the question, of reaching forever toward the horizon of understanding. These cosmic laboratories have escaped the pages of physics journals to become icons of our collective imagination. Black holes now loom large in our culture, not just as scientific objects, but as powerful symbols of the unknown, of transformation, and of infinity itself. Filmmakers and writers have long been drawn to their metaphorical gravity. The movie Interstellar gave us Gargantua, a swirling leviathan whose depiction was guided by the rigorous physics of Kip Thorne, resulting in a visually stunning and scientifically grounded portrait that felt both terrifying and awe-inspiring. In literature, black holes often represent existential voids or portals to profound change, gateways that characters must confront to be reborn or to gain a new understanding of the universe. Visual artists, too, are captivated. One striking contemporary installation uses suspended glass spheres and carefully projected light to recreate the gravitational lensing effect, allowing visitors to walk through a room where the very space around them seems to warp and bend, mimicking the way a black hole distorts the starlight behind it. This transforms an abstract astronomical phenomenon into a tangible, sensory experience, making the physics feel immediate and personal. The resonance extends even into sound. Composers and data scientists have begun to sonify the cosmic data we collect, taking the gravitational wave signals from black hole mergers and translating them into audible frequencies. The faint chirp that signaled the first detection becomes a musical note, the ripple in spacetime transformed into a haunting chord that we can not only analyze but also feel. This cultural journey reveals something fundamental. The black hole's power lies in its duality. It is a real physical entity described by mathematics, and at the same time, a blank canvas onto which we project our deepest questions about life, death, and what lies beyond. They inspire creativity across every human discipline because they touch on universal themes, reminding us that the quest to understand the cosmos is inextricably linked to the quest to understand ourselves. Our journey has taken us from the precipice of the event horizon to the theoretical fires of the singularity. We have navigated the quantum puzzles of information and holography, and witnessed the birth of gravitational wave astronomy. While a definitive answer to what lies inside a black hole still eludes us, we are no longer staring into a complete void. New tools are illuminating the darkness, from the cosmic listening posts of LIGO to the digital universes built inside supercomputers. These are not separate paths of inquiry, but a single, converging effort to understand reality at its most extreme. Black holes have become our ultimate cosmic laboratories, the only places in the universe where the two great pillars of modern physics, general relativity and quantum mechanics, are forced to confront one another. Their immense gravity warps space and time, while their tiny cores demand a quantum description. Unlocking their secrets is the key to a unified theory of everything, a framework that would explain the cosmos from its grandest scales down to its most fundamental grains. This grand quest belongs to all of us. Every new image from a telescope, every chirp from a gravitational wave detector, is a step forward. The great astronomer Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That something may well be hiding within the heart of a black hole. Stay curious, follow the discoveries from great observatories and research institutions, and share your wonder and questions below. The cosmos is vast, and its greatest mysteries continue to beckon, inviting everyone to be part of the next great revelation.